Okay, so today I thought we would look back at this idea of a projectile that can bounce and kind of revisit a problem that we had started working on earlier, looking at a projectile that went through the air, hit the ground, and then immediately lost all of its vertical velocity and just slid the rest of the way. And okay, that's fine, but I think we can do a little better. So let's now go ahead and consider that same question, except now we're going to introduce a coefficient of restitution. So this ball, or whatever this projectile is, can bounce, but when it bounces, the recoil velocity doesn't have the same speed as it started with. For example, since we're dealing with an infinite object being the ground, the coefficient of restitution is just going to be the magnitude of the velocity immediately after the collision in the y direction perpendicular to the ground, divided by the initial velocity just before the collision, which of course is a negative number, again in the y direction. And we'll again take use of the impulse momentum theorem. We'll have to write down kind of two copies, one for x and one for y during each bounce. And then we'll have to remember that there is friction with the ground. This problem becomes a little weird if you don't include friction, and we'll see kind of how that works in a sec. So let's start by applying the impulse momentum theorem to, say, the first bounce here. So what do we know? The change in momentum, and let's just look at the x direction first. So the mass of the object times its final, meaning velocity component after the collision, x component, minus the initial, which will be Vx right before the collision, that's the change in the momentum, is supposed to be the integral of the force component in the x direction. Well, there is a force in the x direction, and it's friction. Now, we know that the frictional force, first of all, it'll be to the left during this collision because the incoming velocity has a forward component. And then we'll have our coefficient of friction. We're imagining static friction here, so during the impulse, I'm imagining there's no real skidding. Doesn't really change the problem much if there is, but let's imagine a static friction. I won't delineate between them. Times the normal force, and this normal force is not just mg, it's greater than mg because it's accelerating or it's changing its velocity. We don't really know how that depends on time. I'll put n of t here, and we've got to integrate this from whatever the time interval of starting to ending for this collision, maybe I'll call it 0 to tau or something like that, would be. It's going to turn out not to matter. We've seen this before, but just reminding you where that came from. And then in the vertical direction, well, I'm going to have my outgoing y velocity minus my ingoing y velocity. The only force that's acting here is the normal force. You might say, well, also gravity. It's true, but let's assume that the normal force is going to contribute a much larger component to the net force in the y direction than gravity. So we can safely ignore the weight of the ball during the collision. Normal forces are usually much larger than the weight during a collision, but it's in the positive direction. So again, they'll be sort of the same integral, but this time it's just m. Okay. The trick here is to now note that mu and negative sign are constants, and I can pull them out of this integral. And even though I don't know what this tau is, I don't know what this normal force as a function of time is, if I divide these equations by each other, that impulse from the normal force completely cancels. And I get something kind of nice. What do we know? The m's will also cancel. So I'll have vx prime minus vx over vy prime minus vy on the left, and I'll just have minus mu on the right. So that's kind of nice. Now, unfortunately, there are kind of a lot of unknowns here. Typically, what we're going to want to do is rewrite vx prime and vy prime both in terms of vx and vy. We do still, though, have this extra factor of the coefficient of restitution that we can use. Now, let's be really careful about all the signs here. E is supposed to be a positive number. That's why I took absolute values. Vy prime is positive because after the bounce, it's upward, moving upwards. But Vy itself is negative. So to cover all of that, I can just write this as this negative, because now it's a negative negative, which is positive. So that's convenient too. So putting those together, I have two equations. I have that Vx prime minus Vx is equal to minus mu times Vy prime minus Vy. And I also, from this, have Vy prime equals minus E times Vy. Okay, now what we can do is try to make this into something like a recurrence relationship. Remember that these Vx prime and Vy prime are supposed to be the velocities of the bounce right afterwards. Yes, we have been using Vy indicating the velocity right immediately before that bounce, but of course by symmetry that's also going to be the negative of the y velocity right after the previous bounce. So I'm going to now make the replacement that Vy goes to negative Vy, so that this is now the vertical velocity of the previous bounce. And if we do that, we get this new relation that Vx prime, and I'll move this other Vx over. What do I have here? Well, like I said, Vy is now going to stand for the positive number, the Vy coming off the ground previously. So this will become a plus, and I can use this relationship with Vy prime to replace Vy prime with this minus Vy. And so when all is said and done, I'll have a minus minus, well, I should say those two minuses give me a plus, but then I'm changing the sign back, so this will be a minus, but it'll be mu times 1 plus E times Vy. So make sure you understand where all those negative signs went. And then finally, I have Vy prime now, again making the same substitution here, will be positive E times Vy. So we can see this nice relationship between the, well, speeds, the magnitudes of the velocity components after the bounce to before the bounce. And in fact, if you're curious, we can divide these by each other. Let's do this one divided by this one to get a relationship between the angle of bounce immediately after versus immediately before. So dividing this by this, what do I have? Remember that this is going to be V prime sine theta prime over V prime cosine theta prime, where this prime just indicates the speed during this secondary bounce. And then on the other side, I'll have E V sine theta, so no prime here, divided by V cos theta minus mu times 1 plus E V sine theta. And what does that become? Well, the V primes cancel. I get a sine or a tangent of this new bounce angle. And then what's the cleanest way to write this? I'm going to divide everything by a cosine here. The V's all cancel. And we get this relationship here. So this tells us that the bounce angle does change. Okay, this angle here probably gets smaller and smaller. Maybe it gets higher and higher. Well, we'll figure it out, but notice that the bounce angle must change if there's any sort of friction. Now, if mu equals 0, if there's really no friction, actually, even then, we're still going to have this coefficient changing the bounce angle. So we really can't assume that this thing always follows the same bounce angle. These aren't just little smaller copies of the same shape of parabola over and over. They get flatter and flatter. Okay, so now we want to look at this as a recursion relation. So I'm going to write this like this. Let's say we've got Vx n plus 1. So this will be the n plus first bounce horizontal velocity. Vy n plus 1. And I'm going to write this as a little matrix. And I want to write this as some 2 by 2 matrix times Vxn, Vyn, which are just these Vx's and Vy's of the previous bounce. And you can see that, well, we've got a 1 here, we've got a 0 here, we've got an E here. This thing right here is a little irritating. I'm going to call this combo together eta. It's sort of some sort of effective coefficient of friction. So it's got the mu, but it's also got an E in it. And in that case, we have minus eta in this upper right corner. And now what we can see is, if I want to get the next bounce, all I have to do is multiply the previous velocity components by this matrix. And then I can trace this back into the past however many times I want. So for example, this will be 1 minus eta 0e squared if I want to trace it back to the n minus first bounce. And sure enough, we can do this all the way back to the beginning, so that at the end of the day, the velocity of the nth bounce is going to be this matrix, I'll call it matrix A, to the nth power times the initial velocity components. And presumably we know what those initial velocity components are in terms of v naught and theta naught. Okay, so our goal is now to try to find some sort of closed form expression for what this power of this matrix is. Let's bring this up to the top and we'll see where to go. Okay, so now what we want to do is we want to try to find a closed form expression for this power of this matrix. Now there are a couple ways of doing this. One way is to recognize that this is a diagonal matrix plus a nilpotent matrix, and then try to work out some generalized sort of binomial expansion. We want to be a little careful though, because matrices don't commute. So the binomial theorem for matrices looks a lot more complicated. So instead, let's just look for a little bit of a pattern and then prove it by induction. I'm not going to do the proof by induction itself, but let's look for a pattern and then you can check that this works. So already we can see that a to the 0 is just going to be the identity matrix. A to the 1 is this matrix. A squared is going to be this matrix times itself. So if we try that out, what do we get? Well, this first one is just going to give me a 1. This second column is going to be a minus eta e. So I'm going to write that as minus eta times 1 plus e. This third entry down here will just be 0, and then this last entry will be an e squared. Okay, interesting. Let's look at a cubed. And a cubed, of course, will just be this matrix we just got, which is a squared times another copy of A. All right, let's work that out. So the first one is still giving me a 1, so I'm starting to think that the first upper left entry is always 1, and it is. The second entry is the nasty one, so I'll have a minus eta, and then a minus eta times 1 plus e times e. So that's minus eta times the 1 from here plus e times 1 plus e. That's e plus e squared. Okay, this lower left is going to be a 0. I'm starting to think that that's always going to be 0, and it is. And this lower right is going to be e cubed. I'm starting to think that's going to be e to the n, which it is. So my conjecture is that a to the n is going to be 1, 0, e to the n. Those are the easy ones. They follow a nice pattern that we can see. For the upper right corner, I've got 0, minus eta times 1, minus eta times 1 plus e, minus eta times 1 plus e squared. I think you see where this is going. It's going to be minus eta times 1 plus e plus dot, 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 plus e to the, what, n minus 1. And you should recognize that as being a finite geometric series, which means I can write this whole thing as 1 minus e to the n over 1 minus e in the upper right-hand corner, again, times minus eta. If you want to leave it like this, you can, I guess, but this is going to be the cleanest way to write that out. And now I'll leave it to you if you want to prove this by induction. Go ahead and do it. It's very trivial. This can, like I said, also be gotten by looking at this as a sum of a diagonal and a nilpotent matrix and then working out the binomial theorem expansion. But it's a little trickier because you have to worry about commutativity of matrices. Okay, so now that we have how Vn depends on V naught, I'm ready to try to write down something like the total range of this whole object. So let's call this R1, R2, R3, dot, dot, dot. And notice that, of course, that's the difference here. So R2 is just this bit, R3 is just from R2 to R3, etc. The total range is going to be the sum as n goes from, well, let's count carefully. And actually, just to make this a little more clear, I think I'm going to start at 0 here. So I'll call this one R0 because it's determined by V naught and theta naught. And then I'll call this one R2 and R3 and R1, R2, R3, etc. So it's going to start from n equals 0 up to infinity of Rn. That's the total range, adding together each one of these. We're hoping this sum will converge. We'll see that it will under particular circumstances. But I need a formula for the nth range. Now, we've derived the formula for a parabolic arc many times on this channel, but I think we're not going to want to use the one that involves trigonometry. If you do use that one, it's got like a sine of 2 theta. Remember, theta is changing very non-linearly, by the way. I erased it, but the part that has the tangent relation tells you the tangent of this angle is going to become very nasty very quickly. Instead, there is an alternative version for the range written purely in terms of the x and y components of the velocity. And that is 2 Vx naught Vy naught over g. And indeed, you can go back and look at our derivations, and you can see that this is really what comes out of setting, whatever you want to call this, y equal to 0 at the flight time. It depends on both of these. We just typically replace this with V naught cosine and V naught sine to get our thing. We're going to leave it this way. That means that this total range is going to be an infinite sum of 2 times Vxn Vyn over g. And now I have formulas for Vxn and Vyn separately based on this matrix. Just in case you're wondering, that tells me that Vxn and Vyn, I guess I'm dropping the little parenthetical superscripts here, are going to be this. So 1 minus eta, 1 minus e to the n over 1 minus e, 0 e to the n, times the initial velocities, which are V naught cosine theta naught and V naught sine theta naught. So you can see this is going to be a kind of messy, complicated sum, but it'll turn out that the sum can actually be evaluated. 2 and g can come to the front because they're constants. And now I need to write these down. Okay, Vxn is this row dotted into that column. There will be a V naught attached to it. And then I will have what? Cosine theta for the first bit, and then minus eta over 1 minus e, 1 minus e to the n, sine theta for the second piece. That's just Vxn. Luckily, Vyn is a lot simpler. That's just going to be V naught e to the n sine theta. I guess I should put theta naughts on all of these. Okay, let's see if we can simplify this a little bit. V naught is a constant. There's 2 of them. Pull them to the front. Sine theta naught, that's a constant. Let's pull that to the front too. Let's also pull out a cosine theta naught from both. That'll leave me a tangent here, and I'll have a sine theta times a cosine theta times a 2, which will give me kind of my good old-fashioned singular expression for R naught. What's left behind? Well, let's see. We're going to have an infinite sum. There's an e to the n still lurking around. Can't pull that out. And then inside these parentheses, we pulled out the cosine. There's a minus sign. I'll put an eta over 1 minus e, and I'll also do sine over cosine out here, which is tangent. And then we have this little binomial that also depends on e to the n. So this is actually just a sum of two geometric series. You got to be a little bit careful about how that all parses out. But if we were to, say, group this into two different terms, this bit will become, actually, the sum is going to be the same, so I'm not going to bother to rewrite that. But the bit that's inside the summand, or the summand itself, will be what? All of this stuff, not including that, is a constant, a singular constant, doesn't depend on n. So all of that will be some constant, 1 minus eta over 1 minus e tangent theta naught. That's being multiplied by e to the n. Then there's this extra minus e to the n, which is multiplying this, which is multiplying another e to the n. The minus minus will become a plus. I have this same messy constant out front, but now I have an e to the 2n. So we do see the sum of two different geometric series here. One has a common ratio of e, one has a common ratio of e squared. And we know what the formula for the sum of a geometric series is. Remember that if I have something like the sum of, I'll just write it as e, why not, to the n, as long as e is less than 1, that's the convergence ratio or radius here, we're going to have, well, it's the first term, which is e to the 0, divided by 1 minus the common ratio. Okay, since I've kind of run out of room at the bottom here, let's bring this up to the top, and I'll write down what those sums are. Okay, here it is with no real simplification. I just went ahead and made the geometric series substitution here, and then the same one with the e squared common ratio for the second term. Let's go ahead and just rewrite this one last time. I'll call that whole thing in the front r naught. And then notice that we could probably find a common denominator of 1 minus e squared. Multiplying that all out, what do we get? I also, by the way, can go ahead and sub in what this eta term is. And when all is said and done, I get 1 minus e minus mu e tan theta naught all over 1 minus e quantity squared. Okay, so where did that come from? Basically, it came from finding a common denominator of 1 minus e squared, but then remembering that this eta has some 1 plus e's in it. That can be factored as a difference of squares, and you end up picking up two of them, one from here and one from here, in all the terms, and then the rest just sort of cleans up with extra algebra. So that's kind of interesting. It does depend somewhat non-trivially on the coefficient of restitution, and then also on the coefficient of friction here. As a final step, why don't we go ahead and try to maximize this range? So setting 0 equal to dr d theta naught, just asking what angle maximizes this range, what initial launch angle. We can see that most of this is a constant. Well, not actually all of it. So don't forget that this r naught does have a theta naught hiding in it. So let's see what we're going to get. We'll get v naught squared, derivative of sine is going to be 2 cosine of 2 theta naught over g times all this junk, plus this same thing, which is v naught squared except with a sine. And then the derivative of this will have a tangent here. I'll pick up a minus mu e over 1 minus e quantity squared, and derivative of tangent is secant squared. Okay, we can see that the v naught squareds and g's cancel everywhere. And then I'm going to go ahead and move this term over to get rid of the negative sign. I'll also go ahead and divide out by the cosine to give me a tangent. So when all is said and done there, I'll have what? On this side, I'll have this thing squared with a secant attached. I'll also have this bit, which will be a tangent of 2 theta naught. Got to be a little careful there. On the other side, don't forget there's a 2 lingering here. And then I've got all of this junk. I'll go ahead and separate it out. So one of those will cancel. And then this term will look kind of like the other side. Okay, now how do we go about solving this? Let's go ahead and clear the denominators. Okay, that'll be a little cleaner to deal with. And then let's also add this over to the left, noticing that there's a mu e that can come out of everything. And there'll be a plus sign and a 2 here. Okay, so let's simplify this a little more. I'll divide the mu e over, and then I'm going to write everything in terms of tangent. I think that'll be the easiest way to do this. So secant squared, and I'm just going to use a little t for tangent, so I don't have to keep writing it. So I'm going to have 1 minus t squared. 1 plus t squared. That'll be secant squared. There's a double angle formula for tangent that lets you rewrite it as this. So it's tangent plus tangent over 1 minus the product. And then we'll have a plus 2t. And all of this is 2, 1 minus e over mu e. Alrighty, what's the next thing we can do? Finding a common denominator here lets us put everything over a 1 minus t squared. Here I'll have, when I multiply it out, 2t minus t cubed. And then here, when I multiply it out, I get 2t minus 2t cubed plus 2t cubed. And you can see that these 2t cubed terms cancel. So I have a 4t over 1 minus t squared. Now I'm going to reuse my double angle formula for tangent and rewrite this as 2 tangent of 2 theta. So that does actually simplify. Phew, okay. Now let's just set this equal to this. Notice that the 2's will cancel out front, and we end up with our maximal or maximizing angle, which is tan 2 theta naught should equal what? 1 minus e over mu e. Okay, now of course there were a lot of assumptions that went into this. So notice of course that I've got a lot of places where I can't let e equal 1. Maybe there's a limit where e can approach 1. Of course we know then that it'll just sort of not decrease its vertical component of the velocity. However, there is still a mu, so even if e equals 1, the friction might stop it from continuing to the right. It'll just sort of eventually stop and keep bouncing up and down in one location forever. So the range could still be finite if even as e approaches 1. However, we should also notice that there was an assumption baked in to this range formula, and that is, I said that the angle got lower and lower, and it may, but remember our original result for the tangent of this angle, which, let me just erase some of this and bring some of our results up to the top. Okay, so here we've summarized some of our results here. We've got our velocity components at the nth step. We've got our total range, which involved the summing of those geometric series. We've got our angle that maximizes the total range, is this particular initial launch angle. And then here's something, I'd written it down earlier in terms of just the velocity components of the previous bounce. But now that we have this general formula, I can write those down explicitly to tell me what the tangent of the bounce angle is on the nth bounce in terms of the original launch angle. And we see that we could have a problem here because this denominator could equal 0. Maybe that's not so bad. Arctangent of infinity is kind of well defined. But it could also be negative, which would really maybe be a problem. Because we know that when we're summing this thing up, we're expecting the range to be a sum of positive terms. But if it ever actually starts bouncing backwards for some reason, that'd be a problem. And in fact, it really shouldn't ever bounce backwards. Once the frictional force has applied enough impulse to cease or to remove the x component of the horizontal velocity, or the horizontal velocity component, it should really just sort of bounce up and down in place there. In other words, as soon as this thing does equal 0, we're going to get a theta of pi over 2, meaning it's just going to bounce straight up. And thereafter, I expect to continue a pi over 2 and not keep on including this formula, because then, well, tangent is no longer well defined. It's infinite. So what we really want is for this denominator here to be non-negative. Maybe it could be 0 if you're willing to interpret this as sort of it stops going horizontal and just sort of bounces up and down until it settles. But if I set this denominator greater to 0, it places an additional constraint on my eta or my n's and thetas. So let's work out that inequality real quick. And I'm actually going to solve this inequality for n, the number of bounces, which I absolutely know has to be a non-negative number. And so what can we do? All right, I'm going to subtract this over, get the negative of both sides, because we know that the negative here and the negative 1 will flip the inequality. And I'll multiply by 1 minus e, which we are assuming is a positive number. And I'll divide by the tan theta naught, which is also assumed to be positive. So if I do all of that, I'm doing it quick, I know, I'll end up with a flipped inequality. There'll be a 1 over eta times all of this stuff, reciprocated. Okay, now I'm going to do the same deal. I'll subtract a 1, get rid of the negative on both sides, and then take the natural log. Natural log is a monotonic function, and in fact, it's increasing, so it'll preserve this particular ordering. That tells me that after subtracting and moving this over, I'll end up with a greater than or equal to symbol, and I'll have the natural log of what? 1 minus this thing. And we know this has to be greater than or equal to 0 also, because n is a positive integer. Well, the only way this logarithm has a positive value is if its argument is greater than 1. So this puts a pretty strong constraint on your initial launch angle. This has to be greater than or equal to what? 1 minus e over eta. If you want, you can go plug in what that is. So that'll be 1 minus e over mu times 1 plus e. So if you want to make sure that this thing never starts bouncing backwards or something, there's a minimal angle that you have to launch it at. If you launch it too low, it will actually eventually start bouncing vertically. Okay, so this tells us the minimum launch angle, or the arctangent of this is the minimum launch angle that ensures that your projectile is always moving to the right, maybe asymptotically approaching a finite value. It's totally fine to launch it at a lower angle than this. It's just that when we went and did this sum, we need to cut off our infinite sum at whatever the value is of n that makes this start to bounce backwards or start to have kind of nonsensical values here. So it'd be a little tricky. You'd have to find the floor of some kind of, I don't know, natural log of this stuff based on what your launch angle is.
And just as one more thing to mention here, here's a little Mathematica code that generated the thumbnail for this and lets us see some of that behavior that we were kind of talking about. So real quick walkthrough of the code. I loaded this MathLatex package just because I'm a stickler for nice typesetting, so don't worry about that too much. We're going to do a manipulate environment so that I can adjust these little sliders. Notice I'm putting in G, defined a few variables here. I'm going to stop the number of bounces at something, 10, let's say. We're doing our differential equation solving. Notice that the horizontal acceleration is 0, vertical acceleration is minus G, except during a bounce. We'll start at the origin, and we'll start with some initial velocity components. I'll put it in degrees, and I'm also going to have a variable that's counting the number of bounces. And then I'm just going to use a couple when event triggers to tell it when to change things and also when to stop. So when it hits the ground and it's going downwards, I'm going to do that whole swap where the next velocity is going to be, well, upwards with a coefficient of restitution. And then my x velocity is going to also change. I did put in this max thing just to make sure that it never actually becomes negative, because then it would start bouncing back to the left, and that is not supposed to happen. We can go over the specifics of that in another video, perhaps, why that is. And then, of course, we should update the number of bounces. And then once we reach the number, let's say 10, we'll stop integrating. This little variable here, Tmax, is just finding the end point of this integration. I know that's a long list of different array indices, but it's really digging into this solution variable and finding the end point of that interval of compilation. Just a fast way to get it. Okay, then we'll plot this out with some nice fonts, and we'll add in all of these different sliders. So here's our graphic, and notice that I can change the initial launch angle, of course, to be higher or lower. I can change my initial launch speed. That doesn't really do much to the overall shape, just makes it bigger or smaller. And then these two are the interesting ones. So right now I have it on a very low coefficient of friction, and you can see that indeed the bouncing angle does get smaller and smaller as we go down. It's probably more noticeable even at low coefficient of restitution. But if I start increasing the friction coefficient, we can see, and maybe I'll increase this a bit too, we can see that eventually it does sort of stop going to the right anymore and just starts sort of bouncing in place infinitely until it all of its energy has been dissipated. So we can see that kind of effective behavior of, if there's too much friction, it's not going to keep on going to the right. It'll eventually just reach some sort of maximal range, and we would have to find out how many bounces that is with like a floor function or something. So kind of fun to play around with it, and you can see that it does depend on both E and mu to determine whether it eventually stops bouncing forwards or if it just sort of continues until the energy is completely dissipated.
Okay, so I think that pretty nicely covers this possibly infinite number of bounces, telling us the total range, telling us the angle that maximizes that total range. We played around with some of the changing shape of this projectile as it moved along with different angles. Maybe I'll leave it as a little homework assignment if you want to try to look at how the speed changes with each bump. You know, what is the kinetic energy at each particular point. And if you're interested, maybe also go calculate what is the total time before it finally comes to rest. Is it infinite? Does it diverge? Or does it come to rest, or come to zero height, if you will, in a finite amount of time? You tell me. QED.